All right, let's dive into something that's basically the secret agent of our digital world. Symmetric encryption. It's the invisible shield protecting everything from your bank account to your DMs. So today, we're going to pull back the curtain and see exactly how this whole thing works.
So here's the big question, right? It sounds almost too simple. How can one single, shared secret be strong enough to protect trillions of dollars in transactions and all of our private conversations online every single day? Well, that's exactly what we're about to find out.
To really get our heads around this, let's start with a super simple analogy. Imagine you have a physical lockbox, and you've got one very special key. That key can both lock the box and unlock it. So, if you want to send a secret note to a friend, you'd write it, pop it in the box, lock it up, and then you'd have to get that exact same key to your friend so they can open it. That simple idea? That's the heart of symmetric encryption.
So to put a more formal definition on it, symmetric encryption is where a single secret key does all the work. It's used for both encrypting the original message, the plain text, and for decrypting the scrambled mess, the cipher text. That's why it's also called single key encryption. Both the sender and the receiver have to have the exact same key. Without it, all anyone else sees is just a bunch of digital gibberish.
Okay, so this whole process really just has 5 main ingredients. First, you start with your plain text. That's just your regular readable message. You feed that into an encryption algorithm, which is basically the mathematical recipe for scrambling things. The secret key is what tells that recipe exactly how to scramble it, turning it into the unreadable ciphertext. Then, on the other end, your friend runs that ciphertext through the decryption algorithm, uses that exact same secret key, and boom, out pops the original message, perfectly readable again.
Now, the idea of that one-key lockbox sounds pretty straightforward, right? But the actual locks, the algorithms themselves, well, they've gotten incredibly sophisticated over the years. So let's take a quick look at how we went from the early days to the powerhouse standard we all rely on today. Back in 1977, the big thing was DES, the Data Encryption Standard. But as computers got more and more powerful, its 56-bit key just wasn't enough to keep attackers out. So as a stopgap, we got triple DES, which, you guessed it, basically just ran the DES process 3 times. But the real game changer landed in 2001, AES, the Advanced Encryption Standard. It wasn't just a patch, it was a brand new design, built from the ground up for serious security and speed.
So what makes AES the king of the castle? Well, for one, it supports much longer keys, up to 256 bits, making it practically impossible to brute force. And you'll see it's not a Feistel cipher like the older ones. All that really means is that instead of splitting the data up and processing it in pieces, AES juggles the whole block of data at once in every single round. It uses multiple rounds of complex substitutions and permutations, which is a fancy way of saying it swaps bytes and shuffles them around over and over again until the original message is completely unrecognizable.
And here's the other huge reason AES took over. It is fast. I mean, look at this chart. You see 3DES over there on the left, chugging along at about 10 megabits per second. Now look at AES in the middle. It's more than 6 times faster. In today's world, security is essential, for sure. But if it slows everything down to a crawl, nobody's going to use it. Performance matters. Okay, so we know these algorithms are strong and they're fast and they work on these fixed size blocks of data. But wait a second. In the real world, you're not sending tiny 128-bit messages. You're sending emails, you're streaming video. So how do you encrypt something that's way bigger than one single block?
This is a really important problem. If you just take your big file, chop it into blocks, and encrypt each one independently, you can run into big trouble. Imagine you're encrypting a simple black and white image. All the identical white blocks would encrypt to the exact same scrambled block. An attacker could literally see the outline of your image in the ciphertext. You'd be leaking information without even knowing it.
And that brings us to these 2 approaches. On the left, you have the simple and kinda naive way, electronic codebook, or ECB. It's predictable. If you have 2 identical blocks of plain text, you get 2 identical blocks of ciphertext. It reveals patterns, which is a huge security no-no. But on the right, you have a much smarter way, cipher block chaining, or CBC. Here's the clever trick. Before each block is encrypted, it's mixed with the scrambled result of the block that came before it. It creates this chain reaction that ensures even if you have 1,000 identical plaintext blocks, every single one will look totally different once it's encrypted. It completely obliterates the patterns. We've talked about how strong it is, how smart it is, but for all of its power, symmetric encryption has one giant, glaring weakness. It's the Achilles heel of the entire system.
Seriously, just think about this for a second. This whole thing only works if you and I have the same secret key. But if we're on opposite sides of the world and have never met, how do I get that key to you securely? I can't just email it, right? An eavesdropper could just grab it. It's a classic catch-22. You need a secure channel to share a secret key, but you need a secret key to create a secure channel.
One of the classic solutions is to bring in a trusted middleman. It's called a Key Distribution Center, or KDC. The way it works is pretty clever. Your computer, let's say host A, tells the KDC, hey, I want to talk to host B. The KDC, which already has a permanent secret key for both you and host B, generates a brand new one-time use session key. It then uses its permanent keys to securely deliver that new session key to both of you. And just like that, you now have a shared secret to communicate directly. Once the conversation is over, you throw that session key away.
So, symmetric encryption is fast and powerful, but this whole problem of sharing the secret key, it's its greatest challenge. And this leads to a fascinating, really mind-bending question. What if we could get rid of the problem entirely? What if we didn't have to share a secret key at all? Could you build a system that uses two keys, one key you make public for everyone to see and another that you keep completely secret? Well, that's a story for another time.